Pretend I'm fine, but I know you can hear me sleep talking at night. I tried to hide, lost my mind. All my crooked edges cut me up inside, day and night. My composure ran away, disappeared without a trace. I can't cover up the pain. Hold me and don't ever leave. You're the only good in me. When I lose it, promise you'll find me. Promise you'll find me. Promise you'll find me. Now we wait while I waver in and out of mental states. I can't escape. Watch the flame. It could burn us both if it is never tamed. I'm afraid. Hold me and don't ever leave. You're the only good in me. When I lose it, find me. Promise you'll find me. Promise you'll find me. Find me. Promise you'll find me. Promise you'll find me.
Day by day, desperate fight. My fears are waiting for me at the outside. Overwhelmed, feeling low. I'm the star in this depressing one-man show. Wish I would be able to flee, but I'm not stable. Wouldn't stand a chance, it's just too much to handle. I need an inspiration, another world I have to see. I travel with my portal station to a place of fantasy. Whatever I wanna be, nothing blocks me, I'm free. I'm gonna beat my enemies. As a king or as a knight, I will reign, I will fight until I shine in the night. Why should I stay? Please take me away from the life I don't belong. With might and with force, I'm winning the war. No fears, here is where I'm truly strong. Why should I stay? Why should I stay? Please take me away. All has changed, no time to wait. Orcs and demons lurking, but I'm not afraid. Well prepared, confident, rushing through the halls with the sword in my hand. Getting stronger every hour, casting spells with so much power. People raise my banner, tanks on every castle tower. No quest too hard for me. If you wanna join, just bend the knee. Don't miss the chance of victory. We're gonna make history. Whatever I wanna be, nothing blocks me, I'm free. I'm gonna beat my enemies. As a warlock or a mage, in every era, every age, keeping dragons in the cage. As a king or as a knight, I will reign, I will fight until I shine. Or should I stay? Please take me away. Sometimes I have to keep on breathing in. My lungs are filled with too much pain. All the shadows of the past that I'm so leaving, they held me in my sleepless nights. And I'm drowning in the noise like a free fall, walking along my path for too long. Save myself from the visions in my mind. Save myself from the war I have to fight. And I can take it all away. All of my dreams are fading. Save myself from the visions in my mind. Save myself. And I'm drowning in the noise like a free fall, walking along my path for too long. Save myself from the visions in my mind. Save myself from the war I have to fight. And I can take it all away. All of my dreams are fading. Save myself from the visions in my mind. Save myself. Save
Can I be your star tonight? You fill my soul with light the day we met. I don't wanna leave your side, no. Have me by your side when the sun sets. I hope you'll still want me. I hope you'll still need me 1,000,000 years from now. The seasons are changing, the tonight. You fill my soul with light the day we met. I don't wanna leave your side, no. Have me by your side when the sun sets. I hope you still want me, I hope you still need me a million years from now. The seasons are changing, the nights ever fading. It's time we left the ground. Let's leave for an eternity. We'll sail across the lights beyond the sky. I'll be with you eternally. I'm an addict for your love, it keeps me high, keeps me high. I hope you still want me, I hope you still need me a million years from.
Alrighty, crew. Ooh, I think we're a bit choppy there. There we go. All right. Good afternoon, good evening, hello, welcome everyone to what is emotionally an upsetting day because today is the last day of our content in terms of 1014 BPS. Or is it still staticky? I know it was at the beginning. I saw the waveforms were everywhere. Is it a bit better now? I hope so. I need to find a way to like feed through the mic so I can actually hear it. I know there's a way I can. I just haven't looked at that yet. A little. Ooh, okay. It's still a bit of an issue. Interesting. How are we gonna fix this? Only a little staticky. Yeah, it shouldn't be any staticky though. Bear with me, guys. Let me see if I can figure this out. Let me see what to do. Let me try this. Actually, I should probably do that. Okay, is it a bit better now, guys? Is it? Am I still sort of staticky? Am I still all over the place, or is it not too bad now? That's better now. Okay, good. All right, let me start recording this again here. And here. Okay, so that's all. Yep, that's recording nicely. This is recording. Okay, yeah, sorry about that, guys. Yeah, this is the very, very last week of content for Fundamentals of Biochemistry. So you've all now actually last check, I believe almost everyone had submitted their assignment, which is fantastic. There we go. Yeah, pretty much everyone has submitted their assignment. Look, I'm going to talk more about that in the Shoot workshop this afternoon, just because that's just easier. But yeah, let us get started on looking at membrane transport. So, what are our goals for today? What are we trying to do? We're going to be looking at the selective permeability of membranes, which again, Shouldn't be too difficult. We're not going to be focusing too much on that. We're going to be looking at the main methods in which molecules move, especially across a lipid bilayer. So none of this should be brand new to you guys. You should have learned it in previous courses, but we're just going to sort of recap and rehash on that. We're then going to look at what facilitated diffusion means. We're going to be looking at active transport, secondary active transport, and look at why it is so important and useful within biological systems. So, on that note, let's get started. So, transport across a cell membrane. Now, I've mentioned extensively that, cell membranes are obviously very important for, keeping things out or holding things in, sort of segmenting different compartments of a cell. That's all well and good, but we don't want those walls to be just purely impenetrable. It completely defeats the point. Okay, we want things to be able to move in, we want things to be able to move out, but what is most important there is that we want to be able to control, to the best of our abilities, what we can move in and what we can move out. Now, something that's very important to take note of here is that cell membranes are permeable to small, non-polar molecules. Now, obviously, the lipid bilayer has the hydrophilic head, hydrophobic core, but what can happen is with sort of small non-polar molecules is that they can actually move straight through the lipid bilayer. But again, we're going to talk about that a little bit more in a moment. So transport across this membrane can be facilitated by proteins. Okay, so we can use sort of different pumps or channels or pores or things like that. And typically, these proteins are called transporters or they're called permeases. Now, when we're looking at this, at the membranous transport, the big thing to sort of keep in mind here is just ask yourself, is this process using energy? Yes or no? That's the best way to sort of start this classification process. I do that every time. So the first thing is, if we're looking at the types of diffusion that do not use energy, these do not use ATP. The first one is just regular passive diffusion. Okay, now the definition for passive diffusion is the movement of a solute or the movement of a substance from high concentration to low concentration down its chemical gradient or down its concentration gradient. Okay, it does not require energy, and I'll explain how this happens in a moment. The next one that also doesn't require energy is facilitated diffusion. Now, keep an eye out. Try not to get these two confused, okay, or muddled up. So, facilitated diffusion, it's almost identical to the definition of diffusion. It is the movement of a solute or a substance from high concentration to low concentration down its concentration gradient. That's literally word for word what I set up here. But it is mediated by a carrier protein or channel protein. What this means is that it needs help. It needs a protein of some sorts to transport it across. It's still moving down its concentration gradient. It still does not require energy, but it can't just move through willy-nilly. It needs something to help carry it through. And the last one here is active transport. So this is the, if we're looking at energy consumption, this one is the odd one out because this one requires energy. This one needs ATP in order to work. And we're going to be looking at an example of all three of these. So active transport is the movement of a solute from low to high. So it's going against its concentration gradient. And it's typically done by, the active transport is driven by either sort of ion gradients, or it can be looking at ATP hydrolysis. This one's probably the main one here. So in a nutshell, sort of keeping it nice and simple, this is what we're going to be looking at here today. So you've got our concentration gradient. We've got high concentration to low concentration. Simple diffusion of a non-polar molecule can just move straight through. Or if there's a gap or a hole in the membrane, it can move straight through. However, we can also have these channel proteins here that are channel or carrier mediated. So channel mediated, meaning like a ligand's got to bind to it to activate it, so then it moves through. Or our carrier mediated mean only certain things can fit into this protein before it moves through. Again, I'm going to explain all these more in a moment. Then, of course, we've got active transport. This is going the opposite direction. This is going against that concentration gradient. And because we're pushing it against that concentration gradient, we need to use energy. Now, just looking at this, not a graph, a flowchart rather, what we are essentially going to be looking at here today is we're going to be looking at diffusion, simple. Now, simple or passive diffusion, they mean the exact same thing. I don't care which one you use, just be consistent. We're going to look at facilitated diffusion, secondary active transport, and primary active transport. And that's where we'll stop. I'm not going to worry about transport of membrane-bound vesicles, so endocytosis, exocytosis, or pintocytosis, or phagocytosis, any of those ones. We're just gonna stick to these main methods of transport here. So, molecular kinetic theory is an important aspect that really, shines a light into how passive diffusion works. So, a couple of things that we need to be aware of here is that when we have a gas, when we have a gas that's moving around in a container, the big thing is that it is entirely unpredictable. If we were to look at one gas molecule, we can't predict where it's going to go, okay? But we can predict where many gas particles are going to move. Now, a good way to sort of think about this is imagine that we are in a helicopter and we're looking over a huge crowd, like a massive, massive, massive crowd. Let's say a massive crowd in the streets of Brisbane. Yeah, they've just right in the CBD, everyone is there. It's packed. I cannot just point to one individual person and say, hey, look, see the guy with the backwards cap there? I bet you he's going to move in this direction. But you can predict how the crowd itself is going to move. It's the same thing here. Now, a couple of other things to keep in mind is that the molecules, when they bounce off a container, are completely elastic. Now, what I mean by that is that the molecule will hit the wall of the container and then bounce back off with no energy lost or expended. If I was to turn around and run at a wall, I would not have such luck. There would be a large amount of energy expended by the noise of me smashing into a wall and me falling down and yelling. So these are constantly bouncing. They're constantly moving around within their container. Now, if we were to then heat up these molecules, if I was to say, take this sort of box down here and put a massive fire underneath it. If I was to start to heat this up, what we would notice is that heat will move into the container, okay, that sort of thermal energy. And what will happen is that these molecules then will have an increase in their kinetic energy. They will start to move around faster and faster because they're getting hotter. And because of that, they will then collide and hit with the surface of the container with a much greater force. This is why they always say you never, ever, ever put a deodorant can in a campfire or something like that, just as an instance, because it is a gas that is in a pressurized container, and if you heat it up, it will explode. Now, in terms of how fast these molecules will move, the rule of thumb is that the hotter the molecule, the faster it's going to move. Okay, the more we heat it up, the more energy we give it, it's going to be moving faster. Now, the bigger the molecules are, the slower they are to move. Now, again, a good way to think about this is comparing, say, the energy needed to get a 18-wheeler truck with a trailer up to 50k an hour versus getting a motorbike to 50 kilometers an hour. One will get to 50 kilometers an hour a lot quicker and with far less sort of fuel consumed than the other one, but one is a lot smaller and a lot lighter than the other one. Yeah, so the truck will take way more energy to really get up to speed, just because it's bigger and it's heavier. Okay, so a lot of these things is what we were already explaining before, and it is this molecular kinetic theory that really governs this movement and diffusion of these molecules in a solution. Like it could be a gas or sort of a solute that's being dissolved here. Now, again, it has to be a net movement of Granny versus 18-wheeler when it gets to 50 kilometer faster. Man, my money's on the grannies. Those grannies are ridiculous, man. They will roll you. I'll have to remember that for next time. Oh, dear. So, when we're looking at our passive diffusion or passive transport here, it will always move from high concentration to low concentration until an equilibrium is formed. And what's also important to note is that over short distances, like microscopic distances, diffusion is really quick. It's really fast. But as you move further and further away, it does slow right down. And this really ties back to how we were talking about like hemoglobin and myoglobin and why we even needed that entire complicated system in the first place. Because it's all well and good if it's in a sort of microscopic distance for diffusion. You know, this is why sort of bacteria and other, you know, microscopic organisms don't have a circulatory network and, you know, hemoglobin and lungs and all this sort of stuff. Whereas we as humans definitely do need it because we are far bigger. Where are we? Yeah, so what's also important to note here, again, it will continue to do this until equilibrium is reached. These are just sort of some cool rules of thumb. Okay, now, looking at diffusion, we've looked at sort of movement of a substance. I now want to have a look at a movement of water across a membrane. Okay, there are three main ways in which water can move through the lipid bilayer. The first one is diffusion through the membrane by sort of gaps in the lipid bilayer. Again, this is pretty limited because it's not very often that you see a big gap or a hole in the lipid bilayer. However, it does, it can happen that way. The next one is diffusion through the lipid bilayer by using specific channels. And an example I've used here is called aquaporin. So aquaporin is a protein channel. It's an integral protein that is put into the distal convoluted tubules and the collecting ducts of the kidneys. And what's important here is that when a hormone called ADH is released, so that's antidiuretic hormone, this is released typically, if you've got low blood volume, very dehydrated sort of thing, what your kidneys and inside the nephron will actually do is it will take this protein called aquaporin and will insert it in the distal convoluted tubule and the collecting duct of that nephron for the purpose of increasing overall water reabsorption, so that instead of water that's moving through your nephron in your kidney going straight through into basically your urethra and your bladder to be stored as urine, we are instead reabsorbing that water back into our blood circulation and essentially, we're holding onto that water. This is how, or one way in which we can concentrate our urine. And the third method that water can sort of move across the membrane, whether it's into or out of, is pinocytosis, okay? So essentially, this is just looking at a vesicle that has water in the center of it. Now, osmosis. Osmosis is incredibly, incredibly important, okay? Osmosis is the diffusion or the movement of water from high water to low water across a semi-permeable membrane. Now, you've got to be really careful here because we can look at and define this in two different ways. We can look at it as a water concentration, or we can look at it as a salt concentration. Now, I'm going to present both to you, and I just recommend that you memorize and use the one that you feel the most comfortable with. So, for instance, if we have two water solutions here. And we've got a semi-permeable membrane, meaning that water can move through, but salt can't. And what we have here with sort of solution A is a 20% salt solution. And what we have here is a 10% salt solution. So if we look at this 20% salt solution, that means it's 20% salt and 80% water. And with this 10% salt solution, it means it is 10% salt and 90% water. So what we see is with osmosis, it is the movement of water from a high concentration of water to a low concentration of water, which means it's going to be 90% water versus 80% water. So it's going to want to move this way. Or you can think of it as a low solute concentration to a high solute concentration. So low solute, 10% sodium chloride, to high solute, 20% sodium chloride. Now, again, it can be a bit confusing because it's like low to high for water, but it's high to low for solute. But what's important to keep in mind here is that it's a percentage. You know, if I have way more solute, I'm going to have less. If I have way more solute, I'm going to have far less water in there. Okay, in terms of sort of just pure ratio. So yeah, the movement of water is governed by the solute concentration. And looking at osmosis and looking at osmolarity, that is a huge factor in terms of how we control movement of water in our body and how we detect how much water we actually have. So for instance, in our hypothalamus, we have osmoreceptors in there that essentially detect and measure how salty our blood is, and will, if it's getting too salty, it's basically saying, hey, we're dehydrated. We need to do something about this. And it will, try to retain water by, reducing amount of urine formation. It will make you feel thirsty and trigger you to have a drink. Such as my hypothalamus is doing right now. But yeah, so that is osmosis, okay? It's the movement of water through a semi-permeable membrane from high water to low water, and is really driven by that solute concentration. This one. Now, as I mentioned before, looking at osmosis and looking at the, sort of salt concentration in the body, this is a main way in which the body controls water movement. Now, there are three main areas in the body. There are three main areas in the body in which we move water sort of into or out of. The first one is the intracellular space, so intracellular fluid. The second one is our interstitial fluid. So this is the fluid that is outside of the cell but is sort of surrounding our tissues. And the third one is intravascular fluid. So this is like your blood plasma, essentially. Now, what is also important to note here is the salt concentration of our blood. We have a physiological salt concentration of 0.9%. That is what our blood is. That is what we want. And this is why if you are severely dehydrated, or you've had significant blood loss, anything like that, you go to the hospital and they give you a saline solution, which is salty water. They don't go, wow, he's really dehydrated, let's give him just water. Someone turn on the tap and let's just put water in his veins. That's very bad. Please don't do that. Can I? Oh, I can fit here. Very good. So, there are three new terms here I'm going to describe in terms of tonicity. So again, tonicity is just describing the osmosis or the sort of osmotic gradient that can be generated within living cells. The first one is isotonic. So what does isotonic mean? It means, okay, you've gone to the hospital and they've given you a saline solution that is 0.9%. Good. Now what this essentially is it is the same salt concentration that we are at. So it means, is osmosis occurring, as in the movement of water? Yes. But what is happening is the movement of water into the cell and the movement of water out of the cell are equal, which means the net movement of water into and out of the cell is equal. I hope that makes sense. Again, please let me know, guys. Interrupt me, type something if you're not quite sure. Now, the next term here is hypertonic. Now, what this tells us is that this is when the cell has a lower salt concentration compared to the ECF, okay? Or it has more water inside of the cell than what it does outside of the cell. So what will happen is that by osmosis, water will be dragged out of the cell and will cause the cell to sort of shrink down. So if we look here, this is isotonic, so we can see equal sort of salt concentration, both inside and outside of the cell. So that means water is going to be freely moving in and out, like equally. Now, hypertonic. This is concentrated salt solution. So what's going to happen here is that we can see outside of the cell, there's way more salt. So what that is going to do is actually drag and pull water outside of the cell, and it's going to cause the cell to shrivel and sort of shrink in. And that process is called crenation. In health science, in another course I do teach in, CTR, so cells, tissues, regulation, what we actually do in the lab is that we give a small vial of sort of sheep's blood, and we put that on a microscope slide, and we put different salt solutions, different salty water solutions onto those red blood cells. And you can watch it under the microscope, and you can actually watch this process occur. You can see these red blood cells look sort of nice and plump, like this, and then they just slowly start to shrink in as the water is being pulled out of the cell. This also happens when you're dehydrated, essentially. Is that the water inside of your cells will be pulled out into that interstitial space, and then again, by the same principle of osmosis, it can then be pulled out of the interstitial space into your blood vessels. And it's a constant balancing act between, the fluid balance inside your blood vessels, so looking at your blood plasma, the interstitial space, and inside of the cells. So this is also another big reason why we don't drink seawater. If you are stranded and there's only the ocean and you are very thirsty and you're tempted for a drink, don't drink it. Okay, because it will actually pull water out of your body and will dehydrate you faster because of this osmotic gradient. Now, the next one here is hypotonic. So let's say, again, we're in the hospital. You're very dehydrated. You've been stabbed or something. Okay, you just lost all this blood. You're also dehydrated. So what do we do? Okay, we're not going to turn around and give you a bag of salty water. That will definitely make things worse. In the same sense, we're also not going to just turn around and get sort of distilled water and just put that in your veins. Hey, it's more water. It must be better, right? No. Because what you can do is then have sort of a hypotonic solution. And what will happen is water will move from the outside of the cells into your cells, but it won't stop. It will keep going, okay? It will just, because of this osmotic gradient, it will just pull heaps and heaps and heaps of water into the cell to the point where it will explode. Which, again, is another fun thing to do when you add, I think it was like 0.05% salty water onto the red blood cells. And again, you can watch them you'll sort of go, hang on, where have all my red blood cells gone? I can only just see carnage and bits and pieces because they literally will just pop and explode. Not something you really want happening to your cells. So, hypertonic is when it will shrink and sort of shrivel up because water is being pulled out of the cell. Isotonic is the equivalent salt concentration, so it means there's an equal net movement into and out of. And hypotonic is where there's a higher salt concentration inside of the cell, so water's going to go rushing in. How I personally remember it, okay? These cells here are very round, okay? They're very round. Oh god. Now what else is very round? Hippos. Hippos are very round. So I just think hippo. Hippos are big and round. So hypotonic reminds me of hippos, and that's how you get big round cells. Don't judge me. That's one stupid way that I use to remember them anyway. So yeah, that's our three main sort of tonicities here: isotonic, hypertonic, and hypotonic. Okay, so looking at membrane transport proteins. Excuse me. So we have sort of carriers, we have permeases and transporters, stuff like that. So these will sort of bind the solute or the thing being transported to the transporter, and then what you'll see is sort of typically a kind of conformational change, which will move it either into or out of the cell. And that's what we're looking at here. So, for instance, we've got our carrier protein here. We've got whatever this is being transported, so it's exposed to the extracellular surface. Whatever it is that's being transported will bind to the transporter, conformational change, and it's spat out on the other end. Now, the other option here is looking at sort of channel proteins, and what these will do is sort of form a pore in the cell membrane, so that once it's open, anything that is either a specific charge or a specific size will be able to flood through. So probably the main one that at least I know I've spoken about, but maybe in other courses that you guys have done, would be your sort of voltage-gated channels. So like your voltage-gated sodium, potassium, or calcium channels, like you would see with your action potentials and whatnot. That's a good example of a channel protein. Now, here's something that's very important to keep in mind, okay? What we have here, I will refer to this one. With either channel-mediated or especially carrier-mediated, is these are types of facilitated diffusion, okay? It needs to use one of these two proteins here in order to move from outside the cell to inside the cell. Now, what is very important to keep in mind as well is that with facilitated diffusion, it is saturable. Now, I know you guys are just getting so keen and so excited. Speaking of grannies, here they are again, because we see a lot of overlap here. We see a lot of overlap with facilitated diffusion, as we saw with enzymes. So, because we can look at a transport protein and look at the rate in which it's being transported, this follows a similar method of the Michaelis-Menten equation. We have our Vmax. We have the maximum rate in which a substance is being transported. So if we look at these different terms, and I'm just going to use, say, a GLUT1 transporter. So like looking at a glucose transporter just as an example here. We have Vmax. So Vmax for enzymes was the maximum rate of reaction of an enzyme. For facilitated diffusion, obviously it's not an enzyme, but that same meaning carries across. This is the maximum rate in which this transport protein can move glucose from outside the cell to inside the cell. And then you've also got Km. Now, what was Km? Well, Km was 1/2 of Vmax. Exactly the same with glucose and these glucose transporters, okay? However, just keep in mind, there are, depending on the source that you look up, and this is what I'm saying over here, is that if you're looking at, say, facilitated diffusion, there are different websites or different sources will refer to it as KT, not KM. And I think that's just to prevent confusion between facilitated diffusion and enzymes, but just keep in mind that they are the exact same thing, okay? Km is 1/2 of Vmax, KT is 1/2 of Vmax. And what I'm sort of just trying to show you here is that same theory that applied to enzymes also applies to facilitated diffusion because they follow the same principles. You have a solute, or you have a substrate binds to a protein or enzyme, and something happens, and then it leaves again. And that's what we're looking at here. And you can see the difference in speed, the rate of glucose uptake. Look at the difference between passive diffusion, which, I mean, it's not great. It's not great. Versus facilitated diffusion. Huge difference. Now, something I want to be very clear about so that you guys aren't having a heart attack. When it comes to, kinetics and looking at, KM and Vmax and blah, 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 please be aware that in an exam or an assessment case, I will only give you things like KM and Vmax and KCAT and all that sort of stuff in enzymes, okay? I will not give you anything like this in terms of Vmax and doing any calculations for facilitated diffusion. I 100% think that you all could definitely do calculations like that because it's the exact same thing, but I don't want to murky the waters or sort of make it more confusing or more difficult for you guys. So what I'm essentially showing you guys here is one, the same thing that you learned in enzymes does apply to facilitated diffusion. Two, look at the speed difference or the change in rate of facilitated versus passive. Massive difference. And thirdly, in the same way that Vmax is being achieved with an enzyme because it's saturated, okay? It means it's working as fast as it can. There's no more left for the substrate to bind. The exact same thing applies to facilitated diffusion. It can be saturated. Those are the three main things I'm sort of trying to get across in this slide. Oh, here we go. So you can use the same method taught in enzymes to convert, say, rate. You can do a Lineweaver-Burke plot, okay, or a double reciprocal plot. Again, you can do the exact same thing here, but instead of it being enzymes, it's just facilitated diffusion. Again, I'm not going to quiz you on that, but just please do keep that in mind. So, facilitated versus passive, okay? Passive diffusion, it's still high solute to low solute. So is facilitated, high solute to low solute, but it needs the use of a protein carrier or a protein transporter. Next thing, three main features that differentiate between these two. One, facilitated diffusion is much higher than passive diffusion in terms of its rate, okay? It is much faster. Excuse me. In the same way, too, that we saw with enzymes and the specificity of enzymes, we can also see that same specificity for facilitated diffusion, which our body can definitely use for its advantage. Now, and the third point here is that the transport, because it needs to bind to this protein in order to obviously be transported, it can become saturated. So those are the three main takeaway messages here in terms of comparing facilitated diffusion to passive diffusion. Okay, let's now have a look at the three sort of main classes of transporter here. The first one is we have a uniporter. Again, this should be sort of relatively straightforward. Uni meaning one, okay? So port to transport. So uniport just means it moves one molecule at a time and will typically be down its concentration gradient. So an example here is like GLUT1 transporter, which is kind of what I was explaining previously. The next one is a symporter. So this is where you have the movement of multiple substrates or multiple substances, but they are both moving in the same direction. Antiporter, again, two things are being transported, but they're moving in opposite directions. Now, I'm going to give an example of all three of those, right now. So, GLUT1, looking at GLUT1 transporters, this is the protein that is pushed onto the cell surface in the presence of insulin. So if you guys have had a big, yummy, sugary meal, or you've just had lunch, it's about 2:15. Yeah, let's say most of you sort of had lunch. You know, your body is releasing insulin now because you've got lots of glucose that's being digested and absorbed into your bloodstream, and your body's wanting to take advantage of that. So what it will do is it will push these GLUT transporters into the cell surface, and then we can see here that they're exposed to the outside of the cell, which makes sense because the goal, what we're trying to do here, is take our glucose and move it into the cell. So, what is happening here in terms of the steps, in terms of the pathway, is that glucose will bind to the extracellular surface of this GLUT transporter. Once it is bound, it's going to cause a conformational change. So again, conformational change, meaning a change to its overall shape. And instead of facing outside, it is now facing inside, where glucose will be released. And then upon the release of glucose, it will change its conformation again and face the outside. Nice and straightforward. Now, symporter is where two things are moving in the same direction, but I actually don't want to explain symporters just yet. I'm going to talk about the sodium glucose symporter in a moment when we explain secondary active transport. Now, the last one here is looking at antiporters. So antiporters is when one thing moves in, another thing moves out. So the example I have here is just looking at calcium. So what we see here is the exchange of sodium and calcium, and this is especially important when we're looking at cardiac muscle, because that calcium exchange is very important for the plateau phase of the action potential, to basically allow blood to move through the heart while it's sort of while it's beating, essentially. And again, these systems are incredibly effective. They're incredibly efficient, okay? It can maintain the cellular concentration of calcium at levels 10,000 times lower than the external concentration. So it is really mind-blowing just how effective these exchange pumps are. Okay, so what we've done now is that we've essentially we've spent a bit of time looking at simple or passive diffusion and facilitated diffusion. These are both movement of substances that do not require energy. They do not require ATP. The next one I want to talk about is what does need ATP. Now, something I just want to quickly clarify here, just with facilitated diffusion, the pathway itself in terms of, taking glucose, it binds to the binding site, conformational change, and then glucose is released. Yes, that does not take energy. It does still take energy to create the actual protein itself, to create this transporter by, transcription and translation, the whole protein synthesis thing. That needs energy. We need energy to make it. We just don't need energy to use it. So what we're going to have a look now and focus on is now primary and secondary active transport. Yep, there we go. Good. Now, big thing here again is with active transport, it is moving against its concentration gradient. Okay, it's going from a low concentration to high concentration. Energy is consumed in the process, and we use a lot of energy, okay? On average, just, I wouldn't say napkin calculations, but on, estimated is that around 30+% of total metabolic energy is used only on active transport. That's huge. Take all the total energy that, all the ATPs that you are making in your body, and around 30% just boom, spent straight away on active transport. It is the tax of the biological systems. Now, there are two main types of active transport. We have our primary active transport and we have our secondary active transport. Oh, I can fit there. Excellent. Now, I have two main examples here with primary active transport and with secondary active transport. But I want to try and sort of keep it nice and simple just with this basic schematic for the moment. Then we'll use more specific examples. So here we have our primary active transport. And what is happening... pardon me. So what is happening here is that we have our substance, whatever it is. We're just going to call it S1. Now, we are wishing to move or pump S1 against its concentration gradient. It's a higher concentration outside of the cell than what it is inside of the cell, and we kind of want to keep it that way. We want to maintain that gradient. So we expend ATP and we push our substance out of the cell. Nice and straightforward. And the example I'm going to talk about in greater detail here is the sodium-potassium ATPase pump. Now, here's where things get a little bit squirrely. With that sodium glucose symporter that we looked at, and I basically said, I'm not going to talk about that just yet, I'm going to explain that in a moment. That utilizes secondary active transport. So what is that exactly? Does secondary active transport use energy? Not really. Kinda. Does the movement or does a substance that uses secondary active transport use ATP? No. There is no consumption of ATP in this pump here. But it does rely on a system that needs ATP. Now, what do I mean by that? Let me break that down a little bit further. Let us look at this image over here. Let me do this. So what we see here is the movement of S1 out of the cell. We are using ATP and it's being pumped out. This is the exact same that we saw over here, our primary active transport. Now, what we are establishing with this pump is a chemical gradient. We are creating that S1 is at a higher concentration outside of the cell than what it is inside of the cell, because we are spending energy to pump it out. Now, here's the kicker. We have a new substance here called S2, and it is of a higher concentration inside the cell than what it is outside the cell. But we want to move it into the cell. How do we do it? Well, with this symporter, what will happen is that our S1 will come in and bind to this symporter. And it's going to do this by wanting to move down its concentration gradient. It wants to move from high concentration to low concentration. So our S1 is going to bind in here, then our S2 will bind in here, and then both will move into the cell. So, does secondary active transport directly consume ATP? No. But the movement of S2 is reliant on this S1 concentration gradient. And that can only be established by pumping S1 from inside outside and consuming ATP. So I hope that makes sense. I hope that's not too confusing. It might be a little bit easier once we discuss some examples. Now, the main pump, this one, the movement of our S1, for instance. I want to talk about that in the form of primary active transport of the sodium-potassium ATPase pump. Okay? What its primary function is to establish a sodium and potassium electrochemical gradient to allow sort of our nerves to work, to help generate and propagate action potentials. So what the pump will do is it's going to move 3 sodium ions out of the cell, and it's going to move 2 potassiums into the cell. So it's creating that gradient. So let's go through it and talk about it. So here we have our cell. We have our sodium-potassium ATPase pump. The first thing that's going to happen is that we can see that we have 3 binding sites for sodium, and we have 2 binding sites here for potassium. Now it's exposed to the intracellular side here. And we're going to get 3 sodiums binding to the pump. Once that 3rd sodium is bound, we are going to see a conformational change to this ATP binding site. Once we have that conformational change, it's going to sort of trigger the hydrolysis of ATP to ADP, and with that comes a release of energy, and breaking off that inorganic phosphate. So that phosphate is going to bind to that ATP binding site. And the binding of this phosphate to the ATP binding site is going to trigger 3 conformational changes. And this is important. The first one is probably the most obvious, and that is the sodium-potassium ATPase pump has gone from facing inside the cell to now facing outside the cell. The second conformational change is the binding affinity of sodium to these sodium binding sites here drops. It goes down. Why? Why would it want to do that? Well, we don't want sodium bound to the pump anymore. So by lowering that binding affinity, it's going to get rid of those sodiums. It's the same as what we were looking at with hemoglobin, and how when, the binding affinity of oxygen to hemoglobin goes down, it will be released. And the third conformational change, is an increase in the binding affinity of potassium. So, what is then going to happen is, from outside the cell here, potassium is then going to bind to these potassium binding sites. Once the second potassium has bound to this potassium binding site, a conformational change will occur in this ATPase binding site. And what it will do is it will actually cause that inorganic phosphate to leave, to dissociate. Now, what were the 3 conformational changes that occurred when this phosphate bound, which was over here? What were the 3 things that happened? Well, the pump went from facing inside to facing outside. The binding affinity of sodium decreased, and the binding affinity of potassium increased. Okay, makes sense. So if we go back over here and that inorganic phosphate now leaves, what's going to happen? Well, pretty much these 3 things go back to how they were. So instead of facing outside, it's now going to face inside. The binding affinity of sodium is going to go up, and the binding affinity of potassium is going to go down. So because that binding affinity of potassium goes down, the potassium is then going to be released from that pump, and we are right back to where we started. So that is the sodium-potassium ATPase pump, and I would very highly recommend that we know how the sodium-potassium ATPase pump functions. All right, so guys, that was a lot of info looking at the sodium-potassium ATPase pump. What we'll do, let's have a quick 10-minute breather, stand up, stretch your legs, grab a coffee, do what you need to do, and we will keep going. We'll resume at around 2:35.
Can I be your star tonight? You fill my soul with light the day we met. I don't wanna leave your side, no. Have me by your side when the sun sets. I hope you'll still want me, I hope you'll me up when you're sober, when you showered and changed. You give it up like it's over, but never give it away. And I don't wanna fall for you this time. I can't find the truth in all the lies. If I could, I would believe me. If I could, I wouldn't need you. I don't wanna fall for you this time.
Alrighty, let's get back into it, crew. Let us resume the fun and goodness that is the sodium potassium ATPase pump. Now, again, what we sort of covered here in terms of the cycle of the sodium potassium ATPase pump can be a bit overwhelming, I guess. But what's really important to keep in mind is just the cause and effect, okay? Like, what happened when this phosphate bound to the pump? Well, we had 3 conformational changes, okay? It went from facing inside the cell to outside the cell. Binding affinity of sodium went down. Binding affinity of potassium went up. Now, if you have that memorized, then this makes it a whole lot easier, because when you get over to this step over here, you can just remember, well, okay, if that inorganic phosphate leaves, then the opposite of what happened over here is going to happen over here. And that is, it's going to face the inside of the cell. Yeah, it's going to face the inside of the cell. Binding affinity of sodium is going to go up, and binding affinity of potassium is going to go down. So that's a cool little shortcut that you can use to help you remember this. Now, what's also important to keep in mind with this sodium potassium ATPase pump is that it is establishing and creating a sodium and potassium electrochemical gradient, or mainly a chemical gradient, I should say, rather, okay, by sort of separating them out. Now, as I said before, that's very important for things like, the resting membrane potential and looking at how your nerves work and blah, blah, blah. But where it's also important is this sodium glucose symporter. Because if I was to rewind back to here, I basically explained secondary active transport as this S2 moving against its concentration gradient because it's able to take advantage of the S1 concentration gradient. So in this example, S1 is sodium. And with our sodium potassium ATPase pump, that is moving against its concentration gradient, consuming ATP. So, if we look here at our sodium potassium symporter, let me zoom in a little bit for you. There we go. And I will do this. So, this right here is our sodium potassium ATPase pump. That's what we were looking at in extensive detail just before. And this is creating our sodium concentration gradient, or helping to establish it at the very least. Then what is going to happen is with this sodium glucose symporter, glucose is moving against its concentration gradient. So instead of just consuming ATP here, what will happen is this transporter will take advantage of sodium. So sodium moving down its concentration gradient is going to bind to this symporter. Then glucose can bind, and once both are bound, they both move through into the cytoplasm. So think of it like you and your friend are at a party, and you both live very close together, or you both live at the university. You live at the student accommodation there, and your friend goes, "Oh, okay, I'm gonna catch an Uber," and they all call up the Uber and they've paid for it, like the good friend that they are. And you go, "Oh, hey, can I get a lift? Can I get a ride with you?" So while your dear loving friend pays for the Uber, you can sort of jump in and grab a free ride. Now, again, does that mean the ride was free? No. Okay? Like, we had to pay for this ride by creating this sodium concentration gradient by using this sodium potassium ATPase pump. This was primary active transport. But because by taking advantage of that concentration gradient, as sodium moves in, glucose can get a free ride. So I hope that makes sense. Everyone, please let me know if that doesn't make sense. We'll probably cover this again in the Tute workshop. But yeah, it doesn't use energy directly, but it does take advantage of a system or pathway here that does use energy. Now, I obviously can't just play these on YouTube because it'll just flag for copyright, but there are some good links here. I believe I have these linked on the Moodle portal as well. There are such good resources that help break down, explain primary and secondary active transport, especially sites like Crash Course. They do explain it really, really well. I highly advise checking those out, just as a diversification of different sources in terms of learning this content. Okay, so this is a good little sort of cheeky summary slide here. So, simple diffusion, passive diffusion, just keep in mind, guys, they are the exact same thing. Oops, sorry, this one. So yeah, simple diffusion, passive diffusion, they're the same thing, don't worry about it. I typically will always refer to it as passive diffusion, but it's just good to keep that in mind. Facilitated diffusion, passive transport. I pretty much never call it passive transport because it's too easy to get them muddled up. I will always call it facilitated diffusion. That's using a carrier-mediated transport or a different transport or protein source in that way. And guys, that's it. 1014 BPS Fundamentals of Biochemistry is done. There is no more new content to be had. Well done, guys. You made it. You survived. I knew you would. Okay, well done. So what we're going to do now, guys, we're going to take 5 minutes, and then we'll jump into the Tute workshop where we'll have a chat about your assignment, we'll have a chat about your upcoming quiz, which is next week, and your end of trimester exam. But look, guys, well done. Congratulations again, and I will see you all in the Tute workshop.
Call me up when you're sober, when you've showered and changed. You give it up like it's over, but never give it away. And I don't wanna fall